about I don't even know what it's called, but it's about tables of integrals and computers and integration. And basically this section says, hey, look, we have all these formulas in the back of the book that you can use to do complicated integrals. But nowadays, you just go to Wolfram Alpha, right? So I don't assign you any homework out of there because, you know, we have technology now, and if you have a tough integral, you just go to computer, right? That's what you do. So as long as you're all aware of that, which, has everyone been onto a computer and typed in an integral? Has everyone gone through that process? Okay, I mean, you should have, no, yeah, right.
No,
so
I only just did it today, like one time. That's the first time I ever did it.
You did it in my office the other day.
No, you did.
You showed me the answer.
No, that was from the freaking app.
Well, the app did it then. Yeah. Same thing.
No, it's not.
It's a computer, right? It's somewhere there's an algorithm running in the background. So, you know, just everyone be aware, technology is there. And most of you, moving on, engineering, if you ever need to do integration, you're going to turn to a computer, right? Okay, so what do we do now? Call it a day. Go bury a fish? No. Now we're going to start the next section, our next idea. So now it's time to talk about, like, what is this all for, right? What is all this that we've been doing, antiderivatives, what is the purpose? And we're going to start it with trying to motivate the idea here of finding areas. Now, this is not like an official section in the book. I try when I do this, I have notes, I'll put them up here. I kind of blend a bunch of sections together, finding areas. So I want you to kind of hit like the major reset button in your head right now. We are starting like very fresh topic here. All right, integration will come in, but just take a step back and think about human beings trying to find areas of things. So very, very early on in the evolution of human thinking, we were able to establish and agree upon what we determined to be the area of a rectangle. All right? I could put square up here. Rectangle's a little more advanced, right? We said if you want to know how much stuff is in that geometric two-dimensional shape, then if you give me two sides, let's just call this x and call that y, then the area we all agree is x times y, right? Just multiply the lengths of the two sides and that will give you your area, right? So we are going to take that as the one thing we do know, all right? Now, then what happened is we said, all right, what if your shape doesn't look like this, right? What if it's a little more complicated? Like what if it's, I don't know, like that, like a triangle. You know, what's the area of this? So we all know the area of a triangle is what? 1/2 base times height or something like that, right? Well, let's see where that came from. All we did is said, all right, this is your height, right? That's your height. And your base is distance from here to here. So how is it that the area of that is 1/2 base times height? Let's try and rationalize this. What you can do is you can make a copy of this. So right-click copy, right-click paste, okay? And here's another copy of it. But what I'm going to do is I'm going to take that copy and I'm going to turn it over. You know what? I'd like to exaggerate this a little bit more. That looks almost like perfect. I want it to be more like this. There we go. Okay, so I'm going to go right-click copy, right-click paste, or control, who cares? Okay, so I'm going to take copy of that, paste it here, and then I'm going to turn it over, like rotate it. So if I rotate it and stick it onto the end of this, I think I overdid it there. Wouldn't it look like that? That's a copy of it flipped upside down. Yes? Okay. Let me draw my little, that. There's my height. Now what I'm going to do is I'm going to come in here with a pair of scissors. I'm going to take that, right? I'm going to cut that piece off and I'm going to paste it right there. So I cut that off, right there to there, and then I paste it right here. And then what have I created? I've created a rectangle, right? And what's this length? That's the height. And then what's this? The base, right? That's base and height. So the area of the whole thing is what? The area of the whole thing is base times height. But didn't I right-click copy, right-click paste? So that's 2 of them. So I want half of that. So the area of a triangle is half of base times height. Does that make sense? Okay, so we can handle rectangles. We can handle triangles. How about something like this? So what's the area of that? Well, now the one thing you are allowed to do is measure things. Like you can measure lengths, all right? You're allowed to do that. So couldn't I just do this? Just break it up into a bunch of triangles? And then just measure the area of each triangle? I could do that. I mean, I'd be out there measuring it. It'd have to be pretty precise, but I mean, I always like to think of this as like when people started to fight over land, right? Like my land, your land. And we were like, this is my border, your border, don't come across that line, right? Like we started to create these geometrical shapes, right? And so we need to measure them in areas, all right? So we can handle that pretty good. So when do things start to get bad? When you start getting curvy, right? So let's start with the most basic shape, which is circle, right? Let's just go with the circle. So how do you find the area of a circle? Well, we all know it's, area is pi r squared, right? That's the area of a circle. If you know the radius, which is the distance from here to here, right? The center to the edge, then pi r squared. We all accept that. We're all happy with that. But where did it come from? Right? So we will prove that. We will prove that formula in this class. All right? We're going to prove it. We won't get to it today, but we will prove that that's true. All right? Now, assuming, let's act like we don't know this. Like, we're human beings. We're trying to figure out what is the area of the circle. How would we go about doing it? And the way that it was done initially was by the Chinese, and they did this thing called the method of exhaustion. And the word exhaustion comes from the idea of how they did it. They said, look, I'm going to do this in 2 different colors. They said, look, they would draw a really precise circle, right? Get something like a needle with a string and draw this really precise circle. And then what they do is they come in here and they would draw inside this circle, they would start drawing a bunch of rectangles. Okay, so they would start filling this up with rectangles. Try and fill in as many of these little gaps as they could with rectangles. Right? Does that make sense? And they could actually measure the area of all those rectangles. Measure, 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 measure. And they add them all up, right? Now, what they determine is that if they add up all those blue rectangles, they're going to have some error, right? They're going to have pieces that are missing. Like that little piece in here is missing, right? Unless they drew a really small rectangle in there. But you can't quite fill it up completely, right? With rectangles, but they can get a lot of them in there. And they'd add them all up. In that area that they would get from all those blue rectangles, that would be smaller than the true area of the circle, wouldn't it? So here's what we could say. The area of the blue is actually less than the area of the true circle. Agreed? All right, so they would say, all right, we have an estimate, but it's a little smaller than the actual area. So then what they would do is they'd say, all right, well, let's take, I don't have a red. Is there a red over there? Herman, can you throw me that red without hurting anyone? Gotcha. Oh, right there? Here we go. Okay, got it. All right, so now what they said is this. It's probably going to be dead. Oh, no, it's working. They would draw this right here. They draw a square around it. Now, do they know the area of that square? And that's obviously too much, right? So then what they would do is they'd start saying, okay, take the area of that square and then start subtracting from it all these little rectangles, right? Got me? And they would so take the area of the big square, subtract all the area of the smaller red squares, and that would give them an area, right? But that area is too much. So what they have now is the area of like the red part. But what they've done is they've squeezed the true area between two numbers. Yeah? And the more rectangles they draw, the more precise the smaller they go, the more this squeezes in, doesn't it? And they were able to get it pretty damn close to create the relationship of this. But here's what they got to. They got to area is approximately 22 over 7r squared. So 22 over 7, see, the Chinese didn't know about irrational numbers. They didn't understand irrational numbers were there. So they just thought every number was a fraction. It turns out that not every number is a fraction. So, did you all hear me? Not every number is a fraction. That's a huge deal, but I won't even get into it, right? We've talked about this. Okay, so look, 22 over 7 you do on your calculator is about what? 3.1428. So it's different than pi, but it's good enough for the first two decimal places. And for most things, that's okay. All right? So that's how they did it, right? I can just like visualize these people sitting in this room, you know, drawing rectangles, trying to get as precise measuring, subtracting method of exhaustion. Right? It's terrible. All right, so that method of exhaustion actually doesn't go away. All right? That's exactly how we are going to do the areas under curves. However, we have two things on our side. We have limits and we have the fundamental theorem of calculus. Those two things are going to save our butts big time. All right? A limit allows us to do what? Let things get arbitrarily small or arbitrarily big or get close to something without actually getting there, right? That's what the limit is. And the fundamental theorem of calculus is going to be a way that we just kind of bring everything together and make things easy. All right, so here's the notes, I guess, for this. This gets us to a topic called Riemann sums. So Riemann is a mathematician. The whole idea here, the motivation for this is the idea of trying to figure out areas of things that are not straight lines, things that have curves. I'm going to skip through that. So, if we wanted to approximate the area under a curve, right? If someone were to give you an arbitrary curve, let's say, that goes from here to here like this, and if I want to know the exact area under this, then I could start drawing rectangles in there, couldn't I? Now, what's important to understand in this picture is that you have to know what the function is, all right? So this is given. That means if you give me an x value, I can tell you how high I am there. Like if you plug in 1, plug it into the function, it's going to spit out 2, or whatever the function says. So you have to know this function. But if that's the case, then I could just pick a point here. I could plug that into the function. That would tell me where I am here, right? And then I could just imagine drawing a rectangle across and down, and I could find the area of that rectangle, couldn't I? And I could do that for another point here. Go up, plug it in the function, then just go over, down. I know how wide this is, right? Because I know the difference between these two numbers. And I could find that area. And I could keep doing this, right? So maybe I have 5 rectangles in there. If I wanted to get a better approximation, I'd need what? 7, 10, right?
Infinity amount.
Yeah, so the idea is that the more rectangles we put in there, right, the better our approximation is going to get. So here's the idea again. Right now I'm trying to estimate the area underneath this blue curve. So what I'm going to do is right now I'm going to put 1, 2, 3, 4, 5 rectangles in there. All right? I'm going to make this a little bigger. Okay, so right now I have 5 rectangles in there. And you can see I'm having the computer do this for me. It's adding up the areas of these rectangles, and it's giving me the estimated area. So the computer is saying right now I'm estimating that area with the rectangles to be 51.36. Now this is the true area, 41.33. Don't ask where that came from yet, but we're off, aren't we? we're too much. And you can see we're overestimating here, 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 here. Lots of error. But if we add more rectangles, just like the Chinese, right? The more rectangles, look what's happening to this number. See that number there? The error, how much we're off by? The more rectangles we have, the smaller and smaller that error becomes. So now instead of those big old chunky things, we have all these little tiny little pieces, right? But shoot, how many rectangles do we have? That's 45 rectangles. There's 70 rectangles. Look, even with 70 rectangles, we're still off by quite a bit, aren't we? Right? I mean, that's 41, 42. We're still off. I mean, it's relative, right? So what would be how could we get the actual area, the exact area, if we could somehow let the number of rectangles go to infinity, right? Have an infinite number of rectangles. But what's wrong with that idea? I mean, what's kind of like counterintuitive about that idea? If there were an infinite number of rectangles in here, then how wide is each rectangle?
Infinitely small.
So as I added more rectangles, what happened to the width of them? They get smaller. So the more rectangles you have, the more narrow they become, right? And so if you have an infinite number of rectangles, then essentially what is the width? It's approaching 0. And if you have 0 width, then height doesn't matter anymore, right? Because area of each rectangle is width times height, width times height. So we have this thing that's, on one hand, we're getting more rectangles, we have less error, but on the other hand, the width is approaching 0. But that's where the limit is so valuable, because in the limit, you can approach 0 without getting there, right? That's what the whole idea of the limit is. Can you let the number of these go to infinity, or said another way, let the width of these go to 0 without actually getting to it? Does that make sense? Okay. So we're going to do like a formal, next class we're going to do a formal torture of how we do this by hand, because it's called Riemann Sums and everyone needs to suffer through it a little bit. All right? But I'm going to I'm going to do a spoiler here, and I'm just going to get you to the end result. All right? Without doing all the Riemann sums. Okay? All right. So mathematicians struggled with this for a long time, okay? And they, trust me, the Riemann sums by hand is not fun, all right? It's not fun. But what was discovered is that there is a connection between the area under a curve and the antiderivative. So here's the final result we get to. Now this is something that we should look at and be familiar with. It's the integral, right? Function dx, but we never had these numbers here before, right? So that's something familiar to us. This we have not talked about. This is the Riemann sum, so I don't want to get into that today. But this equation is saying that the area underneath the curve between two endpoints, A and B, is connected to this antiderivative, or whatever, is connected to the antiderivative of the function. Let me write it. I'm going to write it on the board, and we're going to do an example, then you'll see it, and everything will be great. It's this theorem right here, but I just want to do an example. All right. So let's say we're going to do this. Let f of x be equal to x. And let's look at that on the interval 1, 3. All right, so we're going to draw a picture real quick, all right? F of x equals x. We all familiar with that function? It's the identity function, so it's a diagonal line, isn't it? Goes through the origin like that. Okay, so that's the function. Let's look at it just between 1 and 3. So what is the value of this function at 1? 1. At 1, we're up here at 1. And at 3, where are we? 3, we're up here at 3. Okay, so I just want us focusing here, right there. And I want us to find the area underneath this curve right now, all right? Can you find it without doing any calculus? Can you find this area right here without doing any calculus at all?
Yes.
Yeah, make a square and a triangle, right? So let's do it that way first, just to see that we can get the answer. We have this right here and this right here, don't we? We have two shapes. So how wide is that piece right there? 2. So this is 2 wide. How tall is it? 1. Right, it's not drawn to scale. So what's the area of that rectangle in there? The area of that's 2, right? Okay, what about the triangle? It's 2 wide. How tall? So it goes from 1 to 3, so it's 2. So we have the base and the height, don't we? So the area of that triangle should be 1/2 base times height. So half of 4, that's 2. So that area is 2. So what's the area underneath that curve? 4. Everyone agree? Okay, so the area underneath this curve between 1 and 3 should be 4. Now, I want you to do this. Okay, that everyone can do, yes? But what we're going to do is we're going to add to it this new thing, which makes this thing, instead of what we call the indefinite integral, this is now called a definite integral. This means we're now talking about area. We're talking about a number as an answer, as opposed to, when these aren't here, what's our answer? A function plus c, right? But if we put this in, now what we're doing is we're saying finding the area underneath this function between 1 and 3. So what you do is this. You find the antiderivative. What's the antiderivative of x?
1/2 x squared.
1/2 x squared, right? Now we're supposed to put plus c, right? Yes? I'm going to put it this one time, and that's it. And then from here on out, whenever we're doing these with numbers, I'm not going to do plus c anymore. All right? So we have this, but now we need to somehow account for the 1 and 3. So we put here what's called the evaluation bar. And I understand this seems very disconnected and weird. Just let me go through this example and then you'll see the end result, okay? All right, so what we've done is we've taken this, find the antiderivative, plus c, and then we put this bar here with 1 and 3. Now what that bar is going to remind you to do is plug 3 into this, okay, figure out what it is, and then subtract from that what you get when you plug 1 into this. So I like to look at it this way. It's like two things are going to be subtracted. The first thing is what you get when you plug 3 in. So what do we get when we plug in 3? 1/2 times 3 squared, right? 9 plus c. Yes? And then subtract from that what you get when you plug in 1. So what do you get when you plug in 1? 1/2 plus c. All right, let's see what this is. Half of 9 is 9/2 plus c minus 1/2 what? Minus c again, right? And there are c's cancel. And what are you left with? 8/2, which is 4. So this is not a coincidence that the answer here is also the answer here. That is the fundamental theorem of calculus. All right? And again, I'll treat it more formally when we talk about Riemann sums next class. But I want us to do a few more of these examples. All right? Because I gave us a straight line, right? And I did that so we could verify that the answer we get algebraically from the geometry matches up with what we get here. Right now, you could think it's just a coincidence. It's not, though. Is that a question, James?
Yes, sir.
What do you got?
Is it okay to go ahead and write the integral as the integral, solve for it, and then minus what you solve for, and then write, and then take your value?
Like do them separately?
Like, can you just write them as, so for example, x is 1/2x squared minus 1/2x squared, and then you can put your stuff in? Or do you want, or is it like?
That's notation you wouldn't ever see anywhere. So, I mean, I want you to do what makes most sense to you, but let me do another one with the notation that is commonly used, and then we'll see if you can kind of adapt to it. So let's look at this function, x squared, and let's look at it on the interval, I don't know, let's go 0, 3. All right, so let x be that, and let's look at 0, 3. So if we graph this is a parabola, right? Like this, and we're only looking at the right side from 0 to 3. I should probably stop it here, put a dot. So what we're trying to do is we're trying to find the area underneath here. Now, according to what I just said, and you have to take this on faith because it's the fundamental theorem of calculus, all right? And we're not going to prove that theorem in this class. We're not going to prove it, so you're just going to have to take it on faith. The area underneath that should be the integral, and then here, what numbers am I going to put? 0 on the bottom, 3 on the top. It's always, you know how we, on a number line, go left to right? It's up to down is like left to right. So this number here is always smaller than this number here. Okay? 0 to 3. And then now we put the function x squared dx. There we go. Okay, so what's the antiderivative of this? 1/3 x cubed plus c. But I told you I'm not going to write plus c anymore. And the reason I'm not is because this is now what we consider a definite integral. We're going to have a numerical answer, and the c's will always cancel out when you do the subtraction. So I'm just going to start writing that with this evaluation bar 0, 3. That's just the standard notation. Gives you an opportunity to find the antiderivative, write it down, and then remind yourself you still have to do something. So now we're going to plug in. What goes first? The 3 goes first. Okay, 3 into here would give you 1/3 times 3 cubed, right? 27. And then minus 0 in here, which would give you 0. And what's that? 9. So the area is 9 units. We don't know what the units are here. It could be square inches, square miles, but the area is 9. Isn't that nice? I mean, if we believe that this is true, that's pretty nice, isn't it? Okay, let's do another one. One of my favorites, sine x on 0 pi. Can you all appreciate how powerful this theorem is? I mean, we are able to find areas under curves by just being able to find an antiderivative of the function. All right, let's draw a picture of this. This is the sine function, right? But we're only drawing it between 0 and pi. So it starts out here at 0, goes up, comes down, and that's where it stops, right? That is referred to as one arc of sine. That is one arc of sine. Yes? Not arc sine. That's one arc of the sine function. Now, have you ever wondered what the area is under here?
All the time.
Of course, right? So how would we do it? Well, we just need to be able to find the antiderivative, 0 to pi, of sine x dx. Do you know the antiderivative of sine x? Yes, what is it? Negative cosine x. Negative cosine x. And now the evaluation bar, 0 pi. And plug in, right? Do y'all see how I like to write these two parentheses? Just helps keep track of what I'm doing. Okay, so first I'm going to plug pi in, negative cosine pi. Then I'm going to plug 0 in, negative cosine of 0. Do y'all remember from pre-cal what cosine of pi is? It's negative 1, right? But then it's negative. So negative negative 1 is just 1. Minus, okay, what is cosine of 0? 1, right? Right? So 1 and then minus. So we have minus 1. So what's the area? 2. These are nice numbers. I mean, they're not always nice numbers, okay? But this has always been very fascinating to me, that when you take the sine function and you look at just one arc of it, that the area under it turns out to be a nice number. It just seems odd that that would be the case, but it is. It's a nice number. So how about this? What would be the area under this function? 1/2 sine x. If I just change that to 1/2. Well, what would happen here? Constant in front would what? come out. What would happen over here? Just come out. Happen here? It would just come out, right? So what would our answer be? It would just be half of this, wouldn't it? So it would be 1. All right, I have 10 minutes. Yes?
Is he saying that there's very rarely decimal points?
Oh, no, there's more. It's very rare that we're getting nice numbers right now. Yeah, expect crazy answers. All right, this I just have 10 minutes left, and I may as well just, I've gone so far off the cliff today already that I may as well go for this today. Okay, y'all ready?
Yes, sir.
Deep breath. Here we go. We are going to try and find a formula for the area of an arbitrary circle. Okay? For an arbitrary circle. What is the area of an arbitrary circle? We all know the answer is pi r squared, right? Let's act like we don't know that. Okay, so first of all, if this has a radius of r, let's call it little r, can somebody tell me the equation of that circle? The equation from pre-cal. The equation of this circle. Does this look familiar?
X squared plus y squared equals r squared.
Does that look familiar? Does everyone agree that that's the equation of the circle? Is a circle a function? No, it fails the vertical line test, right? However, could you solve this for y? Yes? Okay, and then you would have to take square root on both sides. So all I'm doing is I'm moving the x squared to the other side, right? And then I'm taking the square root of both sides. So now what this gives us is 2 functions, a positive root and a negative root. The positive root draws the top half of the circle. The negative root draws the bottom half of the circle. All right? So here, check this out. Here's how I'm going to find the area of this circle. I am just going to look at the first quadrant right there. And I'm going to find the area of this. And whatever that answer is, I'm going to multiply it times 4. Agreed? Okay, can you tell me what this function is? Well, no, it's the top corner of this circle, right? Which we said is y equals this, right? But only the positive part. Because the positive part draws the top half, the negative draws the bottom. So isn't this the function?
Yes, sir.
Okay, so this is f of x equals the square root of r squared minus x squared. Y'all with me?
Sir.
Okay, yes?
Wouldn't it be also in quadrant 2?
It would be, but I'm only just going to get the first quadrant. I could get the second one also.
Oh, you have the limit.
What I'm going to do is I'm going to only look at this from what? On what restriction? So where does my x start here? 0. And where does my x stop? Careful, where does it stop? I heard it, r. It stops at r, doesn't it? Stops at r. So I'm going to go from 0 to r. Still there? Any questions? Okay, so what should the area under that curve be? Well, it should be the antiderivative from where to where? 0 to r. Remember, r is a constant, right? R is a constant. Square root of r squared minus x squared dx, right? How do you find the antiderivative of that?
That's a thing.
That is a thing. What is that? That's a trig sub. Because this is a constant squared minus our variable squared. Yes? So what is the trig sub that we make here? The trig sub is what? X will be replaced with a sine theta, right? But what's a for us? A is actually r, isn't it? So this is r sine theta. Okay, then we can just continue. Dx is then going to be r cosine theta d theta. And then we know that the square root of r squared minus x squared should be turning into what? R cosine theta. And now we rewrite the integral, right? Okay, so I'm going to go over here on the side. I'm going to do what I would refer to as scratch work. Because all I'm doing right now is I'm trying to find the antiderivative, right? So I'm doing this without these limits. Okay, what does that integral turn into? Integral, that square root thing turns into what? R cosine theta? And what does dx turn into? R cosine theta again. D theta. Okay, r is a constant. So it comes out, right? R squared can come out? R squared. R squared.
Diameter.
I'm happy to see r squared. Cosine squared theta d theta. Yes?
Yes.
Okay, do you know how to integrate cosine squared theta d theta? Half angle identity, right? Okay, I got to do that up here.
Or is he like
Power reducing. I like power reducing more, but it's okay. All right, so now we're doing this, and then we get a half to come out, don't we?
Yes, sir.
Get a half, so that half comes out. I'm going to put it in front of this. And then in here we should have 1 plus cosine 2 theta d theta. Can we integrate both of those? Sorry. Okay. We can?
Yes.
Okay, we got our constant out front. 1/2 r squared. Antiderivative time. Theta plus 1/2 sine 2 theta, right? Plus a constant.
I was just going to go straight to sine theta. Cosine theta.
Yeah. So that we've done a million times now. And then we have to use a double angle identity right there for this one to get it all back in terms of theta. Or sorry, to get it where we can draw a triangle. So what does that become?
Sine theta.
Sine theta, cosine theta. All right. I'm not even putting the plus c because I know I'm not going to need it. I've got just a few minutes, right? Okay. We got to get everything back now. So what does theta become? What does theta become? Take this over here, solve it for sine theta, so divide by r. Arc sine of both sides. So theta is what? Arc sine of x over r. Okay, plus, now we needed a triangle, didn't we? Okay, I need my triangle. I know I'm going fast, I'm running out of time. Okay, so sine theta would be x over r. So this should be x, right? This should be r, and then this side is square root of r squared minus x squared. So sine theta is x over r, and cosine theta is square root of r squared minus x squared over r.
And then minus all that?
No, okay, so that's the antiderivative, right? Okay, so remember where we were. We were here. We were doing this integral from where? 0 to r, right? And we needed the antiderivative of that. We just found out what it was. It is equal to 1/2 r squared arc sine of x over r plus x times the square root of r squared minus x squared over r squared. That's just these two put together, yes?
Yes.
Okay, that's the antiderivative. Do we all agree? Evaluation bar. Where are we evaluating? 0 to capital R. God, it's about to get really nice. Okay, let's plug in R, and we're replacing what with R? We're replacing x with R. So I need two sets of parentheses here. Okay, so let's plug in R. Plug in R here first. Okay, so we have arc sine of r over r, which is 1, right? And then here, when we plug in, no, I'm missing something, sorry. I wrote that too big. Arc sine of 1 plus, now what happens when we plug r in right there for x? You get r squared minus r squared, that's 0, everything here goes to 0, right? So isn't that all we have for the first one? When we plug r into that, that's what we get, yes? Now let's plug in 0 into this. 1/2 r squared arc sine of what? 0 plus, now what happens when 0 goes right there? Kills that off, so we got nothing there. We're there. We just have to figure out what this is. So back to pre-cal. What's arc sine of 1?
0.
That's saying where on the unit circle is your y coordinate 1? At pi over 2. So that's pi over 2, isn't it? So this is going to be 1/2 r squared times pi over 2. Okay, and then minus what over here? What's arc sine of 0? So that's saying at what angle is your y coordinate 0? 0. So arc sine of 0 is 0. If that's 0 times that, everything's gone. Everything, right? So that's 0. So what's our answer? Pi r squared. Pi r squared over 4. But that was just the first quadrant. So we multiply that times 4, and we get the whole circle pi r squared. I did that all in about 10 minutes. That was so much stuff we've already learned like this semester, right? In one go. All right, so next class, hopefully, I will have mourned the loss of Lenny and be a little more in tune. I'm sorry if I was kind of all over the place today. I apologize. But we will come back and we will start using this antiderivative to find areas under curves. And yeah, you can add that. I put it in the Canvas files, right, as formulas you can bring to the test. So you can add that to your collection. Yes. All right, everyone, have a great day.
Yes, sir. Will you be here available tomorrow morning for office hours?
Yes, I'll be there. Yes.
See you tomorrow morning.
You know what? Do me a favor. Text me because my daughter is not well. She might be admitted to the hospital.
Flu
So
or something?
we don't know yet. She has a